thought I had set that automatically. All right, let's start over now. Okay, so there's going to be about 10 assignments, so more or less one assignment per week, except for there'll be two exams, exam 1, exam 2. So obviously no quizzes that day. Also, towards the end of the semester, we'll focus on a team project. Okay, throughout the semester, we'll be building a toy database that implements some kind of social networking app. So that users can post and folks can comment, and so we'll create the database for that. So we'll all be building the same thing individually, right? So each one of you will build the same thing, but towards the end of the semester, you'll be expected to create teams of either between 1 and 4 team members, and you'll get to choose whatever it is that you want to build. Okay, the focus will be obviously implementing the database. What the data structures are, what the tables, how they relate to one another, yada yada. But we're also going to need some kind of mechanism to interact with this database, right? So we'll need some kind of user interface, right? And we have all sorts of options. It could be a desktop application, it could be a Python application, it could be a mobile application. So for the purpose of giving you a means of interacting, right? I'll have one lecture dedicated at implementing a web UI, right? A web UI that allow you to insert data, retrieve data, query, and whatnot, right? Very, very trivial. I'll give you everything you need. You won't be graded on the user interface because this is not a user interface class, but I'll give you whatever you need for you to interact with the database, right? But the focus will be the design, right? Now for the project, there'll be between 1 and 4 team members, meaning you're free to do it, go it alone. It might be a little bit too much for you to just do it just one person. If you feel that confident enough, then go ahead. I think 4 people per team, I think it's too much. But if you feel that your teammates and you trust them not to slack, and you can guarantee me that at the end of the semester you're not going to be there's not going to be any drama that so and so didn't do the work and I did everything and I'm worried about my grade, right? If you can guarantee to me that there won't be any of that drama, that's fine. Go at it with 4 folks. My experience is that larger teams have problems of communicating. Some folks go AWOL, and so just be careful, right? I think ideally, a team of 2 or 3 is adequate. But if you could go up to 4. You're free to choose whatever topic you want to work on. We will be using MySQL here in class, but for the project, you can choose other things, right? If you want to explore non-relational databases, of which we're going to cover some of it here, you want to use Firebase or Mongo or any other non-relational database, that's totally fine. I'm going to be covering here a UI technology that I use a lot in other courses. I'll be using React.js. But if you feel more comfortable on using any other UI technology for the front end, and again, it has to be super, super simple, just functional, just so that allows you to just interact what it is that you're doing, inserting, deleting, querying, things like that, right? So it doesn't have to be anything fancy. But if you feel confident of using something else, then feel free to do that as well. I will get started as early as possible, even though we have a couple weeks towards the end to work on it. I definitely get started early, right, and decide amongst yourself, amongst the team members, what it is that you want to work on. Okay. So we'll be meeting in this room, not the other room, on Mondays. And again, the expectation is that it'll be here in person, but for any reason you need to be absent, you can't come. It'll be broadcast live on Zoom, and also will be recorded, so for you to take a look at. Office hours, we're gonna do it online on Tuesdays and Fridays at 3:30. And we've been asked to hold office hours remotely only, right? I might be physically here in the university, but I'll be in my office doing online office hours. There is a Piazza link, so you can go there. So these are the 3 TAs, and they've put their own office hours. They're going to be doing 2 hours twice a week, 3 TAs, and they've provided here their Zoom links. I'll be using my personal Zoom link, so you can click that and join when I'm there at 3:30 Tuesdays and Fridays. All right, so let's see. So we're going to be together for the next 14 weeks. Today we're going to be focusing on installing the database. So again, we're going to be using MySQL. Right, it's a very simple, free relational database. It's fairly common to find it in industry. So we'll be installing both the server and the client, the Workbench client. If you've used other clients that you prefer for either Mac OS or Windows that you've used in a lot of you perhaps already worked on this before. So if you feel comfortable using another database client, feel free to use that. But in class and in the assignments, you'll see that we'll be using Workbench. So today we'll install that. We'll create a simple database. We'll show you, just demonstrate real quick how to insert, retrieve, delete, update data, just to get the setup, the development environment going, right? So that you can start actually building things. So that we'll do that today. Probably we'll get started with some material for next week, the UML and designing the database, right? So the steps, the main topics are basically listed here, right? We're going to install the database, then we're going to first design the database. We're going to create the database, query it, update it, and then program it, right? So that's the focus for the first half of the semester, right? And how to mostly just using SQL to interact with the database, how to model, how to convert a text representation of some problem, right? Taking English that it's a very inconsistent, very contradictory language, right? It's ambiguous language, right? And converting that into something that is formal, a formal representation of what it is that our clients might be asking us to do, right? And they might go off on a tangent and talk about things that are completely irrelevant, right? And forget to talk about things that are very, very important, and they will assume that you know all sorts of things, right? And so it is our responsibility to make the right questions when we're interviewing our clients, and mostly, as we'll see, it entails identifying what are the nouns, what are the verbs, right, and what are the relationships between these nouns, and that some nouns are just aliases of other nouns, right? And then deciding, what nouns are actually special cases of other nouns, right? And or which nouns are pieces of or are describing other nouns, right? And so it is our responsibility to, break it up into different classes and tables and fields, and that making all those decisions, right, of how to break it up, like we saw with like the example I saw earlier, right? Why did you decide to break up a worksheet into 2 worksheets, right? We call that normalization, normalizing the database, right? So the act or the process of deciding whether I'm going to use 1 table or 2 tables or 3 or 4, right? That's the process of designing the database, right? And typically we do it first graphically, right, using UML. Unified Modeling Language, or an ERD, right, where we graphically represent all our nouns, right, and we connect the boxes with lines that are represent our verbs, and decide, try to identify that, hey, for every one of these, it's related to so many of those, right? here's an actor and here's a movie, and an actor can act many movies, right? So looks like there's a one-to-many relationship going from actor to movies, but it could also the other way around, right? One movie can have many actors, right? So okay, so there's a one-to-many also going from the movie to the actor, so it's a many or many, right? So how do you represent that? Well, in UML, it's very easy. It's just a line with two stars, right? With two asterisks. Okay, in Java, that'd be easy. You have two arrays on both sides, both ends, right? On SQL, there is no such thing as an array. There's no such thing that allows you to create this these two classes or these two tables, and somehow they're related. You can go from one to many, right? But you can't go the other way around. So you need kind of like a mapping table in between that says, hey, all these actors are related to all those movies, right? So some things that are easy to represent in one language, right, in English, in Java, or some other object-oriented language, is not easily representable in SQL. Right? So there are many decisions that you might need to do that are constrained by the particular technology or the particular technology stack that you decide to go with, and and just do whatever you need to do to use that stack, right? So you'll find us a lot of me saying reify, right? And reify means to make concrete something that might be conceptually true and easily to think about in UML or C# or any other functional programming language or object-oriented language. It's actually not trivial to represent in other languages, right? Like SQL, right? So how do we make something that is conceptually true into something that's concrete, right? And you're using the constraints of whatever technology you use. So reifying is that process of making something conceptual, making it true, concrete. So once we've designed it and decided what the what the best design there is, we'll actually implement it, right? We'll use SQL to create the tables and create the foreign keys and primary keys, foreign keys, and whatnot that represents our UML. We'll notice that certain things that are easily to draw are not actually easy to implement, right? And so we'll see what those limitations are. We want to be able to easily go between all the ways that the data needs to be represented. Data can be represented again in English. It can be represented in SQL. It can be represented in UML. It can be represented in some object-oriented language. It can be represented in XML, right? In JSON. The same exact data, but it can be represented in many different ways, right? And we need to be able to establish, what are the mechanisms that we can easily go between all these different ways of representing data. Obviously, the most interest we're going to be focusing mostly on going from English to SQL, right? That's mostly the focus of the course, right? All right. So once we've created the data, we're going to query the data. We're going to retrieve data, where we doing all the selects and the wheres and the where clauses that allows us to filter out, out of all this data that has been spread across many tables, right? How is it that you now recreate the data, right? How do you extract the data that you have all these actors here, and you have all these movies here? Well, not all actors are acting in all movies, right? So how do I recreate, right, only those actors that act in a particular movie, right? So how do I filter and how do I join, right? How do I extract and recreate the actual data? So we'll talk about that. Then we'll spend some time on updating data and deleting data, inserting, and also we'll talk about views. We're gonna spend so much time teaching about avoiding redundancy because we don't want inconsistency. And usually the way we do that is by splitting a table, right? We decide, oh well, this table's too big. These two fields should not be with these other two fields, right? Because it's breaking some property. And then we split it, and then okay, it's good. It's first normal form, second normal form, third normal form, right? Now what we used to be one big table turns out to be now it's 3, 4 different tables, and that's good. We're happy. There's no way to have redundancy, but we now introduce an inconvenience, right, for non-developers, for the ones that actually use the database, right? if they want to retrieve the data, well, they have to go to this table and that other table and that other table, have to join, make all these joins and foreign keys and primary keys. It's a pain, right? So it usually introduces an inconvenience for the user, right? The developer's happy is that my database is normalized, right? It's perfect, it's beautiful, don't touch it. But nevertheless, at the end of the semester or the end of the year, we need to make all sorts of reports, right? Or either weekly reports or monthly reports or yearly report, quarterly reports. And that usually all those reports entail on retrieving data that is from here and related with data that is over there, and grouping and averaging and adding up and doing all sorts of filtering. And so we want to make it as easy as possible for the ones who are actually using the database, and that's where views come in. Views allows us to create virtual tables. They look like table, they behave like table, but it allows us to provide a virtual representation of the data without removing the beauty of having gone through the trouble of normalizing our data. Okay, it allows us to group together all the data into what we need, such as for a report. All right, so up to this point, have been spending 5 weeks in interacting with the data with mostly SQL, and as we'll see, SQL is somewhat of a declarative language, right? And you say, well, here are my tables, here are my filters, here are the tables that I want. Go get me the data, right? And then the database goes and then collects all the data and retrieves it. But as we'll see, there's a limitation on what can you achieve with a simple language such as SQL, right? But us being developers, programmers, we know that if we had an algorithmic functional programming language, we could do so much more, right? And that's where we're going to spend a lecture talking about how is it that we can program the database, right? The database most databases will provide some kind of programming language where you can have the full power of functional programming languages, right? You have for loops, right? While loops, if statements, branches, switch case, everything within the database, right? But so that everything you would expect of any modern programming language, you will find in most databases will provide you the means for programming. The difference is that whereas the data types of other programming languages are strings and numbers and arrays and whatnot, primitive data types. Here, not only do you have those primitive data types, but now you also have much more complex data types which are the tables themselves, right? So not only can you iterate an array, you can iterate over a whole bunch of tables, a whole bunch of rows in a table, iterate over the fields, and do aggregations and insert data, retrieve data, update data, all the things that you'd be able to do manually using SQL to manipulate the data. Now you can do it programmatically. And so you can put a loop and just iterate over 1,000 rows, right? And then do whatever aggregations you want to make, or even update the rows as you go, right? Anything you would expect with programming. Oh, so that's within the database. You can program right inside of the database. But more interesting is that you can program outside of the database as well, right? With any programming language, right? Either C#, Python, any language you can possibly think of. You can connect to the database, log in, right, programmatically, and then run, send commands to the server, from within Java or any programming language that you can think of, right? In this class, we'll be doing it with Java, and it basically is more or less the same, right? Usually it consists in establishing a connection to the remote server. It usually entails formatting some SQL command as a string, sending it over the wire to the server, and the server responding with some kind of collection of rows that meet the criteria of your SQL statement, okay? And then programmatically iterate over that collection, okay? Obviously, it's a little more complex than that, since the since the world of the database is so much different than the world of programming languages, right? The world of, from the point of view of the database, you have access to, all the terabytes of data, right at your disposal, right at your fingertips. Okay, basically you have the whole file system of wherever you're storing the data. It could be terabytes of data. But from the point of view of a programming language, you only have access to whatever you have in memory, right? As you are running your program, right? Which might be maybe a couple of gigabytes, right? So the notion that you would do a query, right, in the database from a SQL statement, and it comes back with 3,000 rows, right, or tens of thousands of rows that match your search criteria, your SQL statement, it would be impossible to replicate that at the programming language level, right? I mean, you're not going to instantiate 10,000 objects, and keep them in memory, right? If you would consume all your resources right away, right? So there's a lot of magic that's happening behind the scenes that allows you to cache these results, right? Just like the Workbench application, when it comes back saying, oh, there's 100,000 rows that came back with your query, Workbench is not loading 100,000 rows into memory, right? It's using some caching mechanism that allows you to either paginate through the rows, right, showing you maybe 100 rows at a time, right? And as you're scrolling through, it goes on and fetches the next 100, or the next 100, right? So there's a lot of magic that happens that allows you to map the database world, which is huge amounts of data, of persistent data that is here. Even if you shut off the computer, you come back tomorrow, it's still there, as opposed to a program that you shut it off and stops executing, and then you have to restart it tomorrow, right? And so it's the persistent data as opposed to the temporal data, right? It's the ephemeral data, data that comes and goes, that goes into memory and then it goes away, right? It's only in memory just for a few milliseconds, right? And so how is it that you bridge these two worlds? All right, so we'll have our first exam halfway through the semester, and then we'll explore a little farther, right? When we come back from the exam, we'll explore a little more the challenges of mapping the world of the relational database world, right, and the programming world, right? I already hinted at some of the challenges, right, of going from these two different worlds. Okay, but there's many more challenges, right, in many things that we take for granted in object-oriented programming languages. Most object-oriented programming languages will have a very expressive language that allows you to use things such as inheritance, right, specialization, overloading, overriding, polymorphism. Okay, and we use them, we program them with these things, and we take them for granted. Well, these things just don't exist in the relational world, right? The relational world comes from several decades ago, before, it predates the notion of object-oriented programming languages, right? But they're still going strong. And so it's the relational data world is very flat. It's a very flat world, right? You just have these tables, and the only way you can create hierarchies is that records in tables can refer to other records in other tables, right? It's the only way that you can create some kind of hierarchical structure, right? Instead, in object-oriented programming languages, it's very common that you have base classes, derived classes that that are specialized. You can create a whole hierarchy of data that is very abstract at the top, right? And then it adds additional features and properties as you get deeper into the hierarchy. Yes. Well, this notion is completely foreign in relational databases, right? So what happens when you want to map a relational database and you make a query, okay, and now you have to represent the data that comes back. You have to represent it in an app, right? And your application, you have classes and subclasses and subclasses, right? So how do you bridge those two worlds, right? So this world is usually referred to as the having an impedance, right? Like a huge gap between these two worlds, right? And that we still need to bridge. So ORMs or object relational mapping, right, is one of many techniques. It was the most common technique that that attempts to bridge these two worlds, right? I know how, and there's all sorts of tools that says, hey, here are these tables, here's the object world, okay? So create a mapping between the two, right? So we'll spend some time using programming using ORMs. In particular, be a Java ORM, but any programming language will have an ORM solution, right? If you go C#, there will be a C# solution for ORM. If you go JavaScript, or you go Python or C++ or whatever language you can think of, will have an ORM solution, or many ORM solutions, right? It's a huge market. It's a huge industry of folks that compete in this space, right? Of providing all sorts of ways of mapping these two worlds. All right, so then we'll spend one lecture on the client server architecture and data-driven web application, right? Today, or it used to be, that a lot of the content that you see online was static, right? It was mostly brochureware or folks trying to sell you something. Today's applications are mostly very, very dynamic, right? Everything's rendered on the spot, in real time, and it's driven by queries. It's data and relational, data that is related to one another, and all sorts of data that folks are tracking you, right? And they're trying to create all these relationships, trying to sell you something. And so all this content is dynamic, and so we'll explore a little bit on how is it that we do these queries, gets loaded into memory, and then we have to represent it in some kind of user interface. Okay, we'll do some really, really trivial front end, enough for you to then grab this and then go off and perhaps use it for your own projects, right? For your own user interface, right? This particular assignment will not be graded, since it goes off a little bit off the topic for the course, but it is there as a prototype on something that you could perhaps grab and use it for your own purposes for the upcoming project that is coming towards the end of the semester. Okay, it implements the simplest of relationships. Implementing one-to-many, many-to-many, one-to-one, and be able to just display a query in a tabular format, be able to delete, create new records, update existing records, like a details page where you can list all the fields and edit them. The very, very basics that you would need for a user interface. You're welcome to use your own if you prefer and start from scratch, but this should help you to get going. Then we'll spend some time talking about how to optimize databases. We want to make sure that when we make queries, that the response time is reasonable, right? If I ask Google for give it a query, it comes back with I got 3 billion views, right, in like half a second, right? So that's very good performance, right? So how is it that they achieve that kind of performance, right? Do they actually go and search 3 billion pages right there and then, and come back with a result in half a second? Wow, how they do that? So we'll explore some of those techniques. What is it that we can do to improve performance, right? And we'll go back a little bit to what you might have covered in algorithms. Anybody done algorithms already? Okay, yeah. So the big O notation, right? That linear search and all the algorithms that allow you to go from quadratic to linear to logarithmic to constant time searching, right? And that constant time searching is what Google has figured out, right? Doesn't matter how big the database is, I'm always going to be very quick at coming back with a result. How is it that you achieve it? Some kind of indexing, some kind of really huge table, lookup tables, right? So we'll explore some of that and talk about indexing. We'll also talk about transactions. The databases are designed to be used not just by one person, right? You're not going to I mean, obviously in this course, yes, you are going to be the only one using your database. But in if this is a real application, usually your database would be used by dozens, hundreds, thousands of folks, right, doing queries, hitting your database simultaneously. And the database it needs to be designed that in such a way that it can perform, right, and give everybody whatever they want, right. But not only be able to respond to thousands of folks, but also, what if you have folks that are trying to modify the same piece of information, right? What do you do? Are people going to step on each other's toes, right? Now imagine that you're editing a Google document, and somebody's editing the first chapter, and somebody else is editing the last chapter. As long as we stay out of each other's areas, right? Then there's no problem. We can merge those edits, right? But what happens when we start, getting closer to one another, and we start, typing over each other's words, right? So that now becomes challenging. How is it that you merge, different updates to the same piece of information, right? So yeah, transactions is gonna allow us to do that, to be able to separate the changes, be able to synchronize those changes. If everybody's reading the same piece of information, then it doesn't matter, right, how many threads or users come in and read the same piece of information. But if somebody's writing, right, should other people be allowed to read while somebody is writing? Maybe not, right? Maybe they should wait, okay, while somebody's writing. When they're done, they can let it go and says, hey, I'm done, now you can read it. Otherwise, if I let you read it, whatever you read might be stale, right? You might make a decision on data that has not yet been settled, right? So yeah, so we'll talk about that. How do we deal with that? We'll talk about non-SQL databases as becoming more and more popular for as an alternative to relational databases, and we see that this is just exploding on all sorts of alternative databases that are going there. We'll play around with Mongo, and we'll also play around with Firebase. All right, yeah. So right before Thanksgiving, we'll get started on the project earnestly, right? We'll perhaps cover some additional topics that might be useful for you for the project. Also, this gives me a little bit of wiggle room if if we need more time towards the end. But yeah, so by Thanksgiving, I think we should be able to get started on the project. Yeah, so when we come back, we can do some additional based on what folks might be finding challenges with. And then on the 14th week, we'll have our exam. Also, the project is due on that 13th. And the 13th, because the grades are due a week later, and the TAs and myself are going to need at least 1 week to grade those projects. Hopefully, you will be done before then. But definitely, I need to put some due date, right? I know it's the exam is right there and the project's right there, so you'll need to do some pre-planning, right? Planning around the fact that the exam and the projects are due the same date. So I would get started a little bit earlier with the project. Okay. All right. Let's see what else. Yeah. So there's about 10 assignments, which constitute 40% of the grade. Then the quizzes is about 8 quizzes. Quizzes are going to be towards the end of the lectures. They shouldn't take more than 30 minutes, maybe less. It's open book. You just do it on your own, and they're mostly just multiple choice or fill in the blanks. You're not going to be asked to actually code. Same thing with the exams. The exam 1 and exam 2 are mostly just fill in the blanks, multiple choice. Usually I'll give you a whole bunch of SQL statements and say well, which SQL statement does the following, or I'll give you some UML class diagram and you have to see whether it's something wrong, or say that what kind of relationships there are, or complete some piece of code that does something, right? Yeah, the project is 3%, and then 2 exams. Yeah, so the assignments are meant to be worked independently. Yeah, the assignments are meant to be worked independently. The project, obviously, you'll be able to work with your teammates. Yeah, so obviously, don't copy, right? If you find something online that can help you out, if there's some piece of code or something that it doesn't necessarily directly pertain to what you're being asked to do, then that's fine for you to use some other piece of code. Just let me know that it's not yours, and if it doesn't pertain and it just uses, it's a nice little view that makes simplifies things, that's totally fine. Also, you can use any code that we develop here in class that I share with you. Usually, if I have any code, I'll share with you in either in a Git repository, and you're welcome to clone it down and use it for your own purposes. That's totally fine. It's okay that you discuss the problem in general with other folks. That's totally fine. But literally copying somebody else's code, yeah, so definitely not. Yeah, don't put me in the awkward position of having to notify anybody. Unfortunately, has happened. The way I'm supposed to work is that I notify Oscar if there's any doubt, okay, the smallest doubt, all right, that the material is not yours, right? Because presumably they keep tabs on folks. So if they see a pattern in other classes, then they might admonish you. All right, but I don't know those things. They know, so I'm supposed to keep an eye on this. Please don't put me in that awkward position, and the TAs either. I hate getting a message from a TA, then so and so looks very similar to so and so. Okay. All right. Any questions? Yes. Yeah, they're on Canvas. Yep. Yes, you'll need your laptop. You need your laptop when we do the exam, right? And they are here in person. If you can't be that particular day, maybe we can figure out something so you could take it later with a TA office hours or something like that. But please try to be here. Yes.
I think your office hours were listed as 3:30 start time, or does that go till 5:30 or 4:30?
3:30 till 4:30 or 5 or whatever. Yeah. Tuesdays and Fridays. Okay. All right. Let's see. Okay. All right. So the first thing that you'll be asked to do is to download a database. Whether Windows or Mac, right? So you can go to this URL that it's listed here, and there'll be a go to the download page. You can ask for Windows or Mac, and you can select to download the installer. Usually it's an MSI package, right? You can double click and it'll start the installation process. And they'll try to convince you to log in or create an account. You don't have to create an account with Oracle, but you can if you want. You can just skip over to the download. You start the MSI package, and it'll look something like this. So we're going to need to install 2 things, right? So one of them is a server application. This is a piece of software that runs in the background. It has no user interface. right? It's just listening for a network connection, right? Starts up and it's just waiting for somebody to connect to it at 3306, okay? So it's listening on a particular port, and usually it's either installed as a service on Windows, right? So you can go to your services on Windows and it'll be listed there as MySQL Server. Or on a Mac, if you go to the preferences, it'll have an icon for the preferences where you can see that the server is either running or not, okay? In both cases, you want to configure it so that it's always running in the background, at least for this semester. For this semester, have it running all the time, okay? And even when you shut down your computer, when you turn it back on, it'll start again, right? At the end of the semester, you can just shut it off if you want, if you don't want to use it anymore. So it's a SQL Server. And then the other piece of software that we'll need is some client. The client will make a network connection to the server, and it'll be a very convenient way of sending SQL commands to the server, right? It gives you a UI where it gives you a representation of a table where you can enter data, and when you say run, right, it grabs all that user interface, right, and it creates a whole bunch of SQL commands that it's going to send over. It's just a convenient way, so you don't have to type every single exact command, right? Again, whatever client you choose, it'll do something similar. We're going to be documenting SQL Workbench. Okay, so on Windows, it'll look something like this. Download the installer. You can say no thanks, and then just follow the instructions that are listed here. Right, you can choose a custom installation. Okay, present here. And it'll give you a tree like this, where it provides a whole bunch of tools that you can install. Right, we only really need two things. Right, we need the server and we need the client. Right, it's gonna suggest that you install a whole bunch of other tools that we don't need for this course. We only need those two things. So we can navigate down to the SQL Server, and then when we are down to the SQL Server, you can select the latest version and then add it. Then you can go up the tree and then down again to the client, the workbench, right? Again, choose the latest one and add it. Once you've added it, you can say next, and it'll start the installation of both of them. It says, okay, these are the two things that you're going to install. Okay. Standalone. It'll be a standalone running server. So meaning you only have one instance of these things running on your machine. This can also be installed as a cluster of many databases together. We don't need that. That's advanced. So yeah, you just need one instance running on your machine. Then it'll ask you, how is it that it should listen? What port should it listen? The default, leave the default is 3306. That's the standard port for MySQL Server to listen at. Right, just leave the default. Also, choose a strong password encryption and set up the root password. Right, so this is going to be the root password. Don't forget it. You can choose something simple. It doesn't really matter. This is a server running on your machine. It's not like somebody's gonna hack you into your database or anything like that. Right, so you'll be the only one using this database. If this were running on a public server that a whole bunch of people are hitting it, then yeah, definitely don't use something fairly complex. But for you, put something simple you can remember. If you don't remember it, you're gonna have to reinstall. Okay, so make sure you write it somewhere or something that you're gonna remember. Right, so this is going to be the root password. The username is going to be root, R-O-O-T, and the password is whatever you install here. Okay. Yeah, don't forget that password. And all right, so we'll go through and install it, and once it's done, it'll ask you, okay, do you want me to start it up? Do you want me to set it up as a service? And say, yes, I want it to set it up as a service, meaning it'll run automatically when you shut off, when you boot up your computer again, right? Once it's installed, you can go to, on Windows, you can go to services, and if you go down all the way to the M's, it'll be listed there as MySQL 80, and it's configured to automatically restart, whenever you restart the machine. Okay, you can double click it and change it so that it restarts manually, right? So you can manually start it, manually stop it, right? So if you start workshop and workbench, and workbench is not connecting, make sure you come back here and see if the server is indeed running. Okay. On Mac, it's fairly similar. Yeah, you can download from Mac OS. Again, no need to create an account. Instead of an MSI, it'll be a DMG, right? So you'll double click it, it'll unzip, right? And then you can start the installer, the package installer. Because it's a piece of software that is not downloaded from the Mac OS App Store, it'll throw a whole bunch of security concerns saying, sorry, this was not blah blah blah, it's not signed by Apple. You can say, okay, you can go to the system preferences, to the security and policies. If you go in there, you'll see that the package was flagged saying that, hey, I blocked this. I'm scared of this package. You can say, you can open anyway, right? So it'll start the package installer, right? So install that. Say continue. You might be asked to log in and provide your laptop password, right? Just to identify that it's still you. Yeah, that it might ask you to log in again into your laptop. It'll go through the installation, wait till it's running. Same thing, is going to ask you to use the strong password encryption, and it will ask you for the root password. Again, same thing. Don't forget this password, right? The username is root, and the password is whatever you type in here. Don't forget it. Write it down. Once it's done, it will be installed as a service. If you go to your system preferences, there'll be an icon there for MySQL now, and double clicking it, you can see whether it's configured to restart automatically, or you can start and stop, with that button. Okay. All right. Okay. So I'm going to assume you're going to have the database already up and running. Okay, so once it's installed, we'll need to connect to it, connect to the database, and for that we'll need Workbench. Okay, now on Windows, the installer will install both, right? The server and Workbench, right? On a Mac, you'll have to install both of them independently. First you install the server, and then you're going to have to go back and also download the Workbench client and install it separately, right? So the installer doesn't do both, right? Yeah, so we'll use Community Server and Workbench, right? Same thing, right? We have a user, here's you, interacting through Workbench, sending a whole bunch of SQL queries, right, to the MySQL server. When you start Workbench, when you install it, it'll come to this page, and it'll ask you, okay, well, which server do you want me to connect to, right? I just installed it, but Workbench doesn't know. Right? It's not going to automatically connect to it, right? Indeed, Workbench can be used to interact with any SQL server. If it's running either locally on your machine, where we're going to be spending most of our time, or if this server is running, halfway across the world, right? If you know the IP address of the machine where SQL server is running, you can connect to it, right? And you can connect it by clicking, let's create a brand new connection, and it'll ask you what's the IP address of the machine. It'll assume it's 3306, the port number, or you can override it if usually if it's a vendor that you're purchasing the service for MySQL, they'll give you the long URL, right, that contains usually the domain names of the server, right, username, the password, right, the port, right, and then the name of the database, usually, right, if you purchase it either from AWS or some other database vendor. Okay, so the connection, when you click on add a connection, it'll look something like this. You can give it a name, right? And that name is just a descriptive name for just to remember the name of the connection. And then you'll set up the host. The host name this is the actual name of the domain, or it could be an IP address, right? If you know the name of the IP address of the machine where your server is running, you can put in here the IP address. By default, it's 3306. The username, again, this could be either root, right? And then the password that you put in, if it's local on your machine, or if it's something running halfway across the world, it's whatever username they might give you, right? That username. When you test, it'll ask you for the password. The default schema is, as you'll see in a minute, when we start up MySQL, it allows you to create any number of schemas, right? By schema, so schema, the definition of schema is structure. What is the structure? What's the structure of the data, right? Meaning, what are the tables and how are the tables related? How is the data structured, right? And we call that a schema. Okay. We also say we use this, the term schema is kind of overloaded in this course. It's also when we talk about the structure of the data of a single table, we also say the schema of the table. Okay. So we talk about the schema of the database, then it's the collection of all the schemas instead of a database, right? Which are the tables. Okay. So it's the term is a little bit overloaded, but basically in general, it means the structure of the data. Is this a structure of the data of all the tables together, or is it an individual table, or even a field? The schema of the field might be the name of the field and then the data type of that field. Okay, and whatever other constraints it might have, whether it's required, not required, right? Whether it's a primary key or foreign key and whatnot. Yes. All right. Yeah. So we created a new connection. Once we have the connection up and running, we can start interacting with the schema, right? And it looks something like this. On the top, you have a whole bunch of buttons that where you can send commands. Now this looks slightly different on Windows and on Mac. On Mac, the tabs usually tend to be at the top. So you have management and schemas here, and then object info and sessions down below. On Windows, it'll look something slightly different. The tabs are at the bottom, right? But it's basically the same piece of software. Okay, you can do exactly the same thing with one or the other, right? The tabs are a little bit in a different place, right? Just look for it, right? If I'm using a Mac screenshot, right, you should be able to figure out what the equivalent on Windows is. Okay. But nevertheless, the management allows you to do administrative stuff like creating new users, new accounts, things like that. So other than the root user, you can create other users, right? Maybe a user for this course, right, that only deals with the schemas that are for this course, and then maybe another one for your own projects, right? Or another one for your job or something. Okay, so different users for different purposes. Then you have the schemas. Schemas here. This would be a list of many schemas. You can have any number of schemas. Okay. Again, one schema for the assignments for this course. We're going to create one schema that we're going to use the same schema throughout the entire semester. And in that schema, we're going to be adding tables as we go. Right, 2 tables today, 3 tables next assignment, 4 tables later, and as we go, we'll add more and more tables in the same schema. Yes, and usually it's one schema per project, right? So since we're going to be working on a kind of like a social networking project, right? We'll create a schema, and we would call it something that is, descriptive for the project that we're building. Right, so it might be a Twitter database or a Facebook database, or my own great social networking app database, right? And in there we'll have all the tables for the users, and the tables for the comments and the posts and the whatever, right? And then you might have another schema later on this semester, one dedicated for your project, right? So at least at the end of the semester, you should have at least 2 schemas, one for the assignments, right, and one for your project. Right. Certainly, you can have more. You can have, maybe a schema where you just play around, right, and just let me just try something out without ruining my other 2 schemas. Right. So maybe you have like a exercise schema where you can just try something out, where you can, doesn't matter if you break it, right? It's not ruining your other database. Yeah, and also it opens up a window here where you can start sending commands to the server, right? You type your commands, your SQL command, and then you can execute the command by clicking on this this lightning bolt, right? And the lightning bolt will read the whole text in this file, right? And it will send it over to the server, you know, to the wherever the IP address you selected, wherever the port number is, it will connect to that server and send that command, right? It'll typically show you the command before it sends it, and then you say, yeah, that's the command that I want, and it'll send it over. Okay. Same thing with Windows. Okay, schemas. All right, so let's actually let's demo this. Workbench. So I obviously already have my database up and running. Yeah. So here's my connections. So let's create one for, you know, cs5200 fall, you know, 2021. Notice this is the IP address of my machine, right? So it's 127.0.0.1. You know, it's universally referred to as the local host. You can actually use localhost. Right? You can use localhost or 127.0.0.1, meaning it's running on my machine, right? But if it's my friend's machine, right, and I know their IP address, okay, I could type it here. If we're in the same network, okay, and he has opened that port, I would be able to connect to my friend's database, right? That's running on his laptop. Okay, root. I actually don't remember my root password. Oh crap. I know. Your username. Oh yeah, that works. There it is. Oh, that's not it. 200. That one. There we go. I actually created a username called your username because I use that in the assignments where I give you an example and say well, create a connection, and in the instructions I say use your username, right, and your password, and students were coming back that they actually typed your username and your password instead of whatever username and password they might create. So the easiest for me to you know, to help them and to I would import their database, right, and try to log in and blah blah blah, and that was the easiest way to handle everybody's all right, anyway, so yeah, so there we are, and here we have the we can have any number of schemas, and we can create a brand new schema for this course, right? So I can say either I can right click and say create new schema, or there's a button here that creates that new schema. You know, either way, it brings you to a new screen that allows you to create the new schema, right? So I'll create one for this class. I believe in the assignment I asked you to use DB design, right? So I'll call it DB design, and we already have a DB design, so I'll say DB design cs5200. How's that? Okay, and then apply. Okay, so this is going to send a command to the server, right? It's already connected to a server. It has a live connection to a server, right? And to send this command, I could have actually typed this myself, right? At the right here in my query screen, I could have actually typed this myself by hand, right? But still, I'm using a user interface. It writes it for me and it says, "Are you good? Is this what you want to do?" Yes, I'll say apply. Comes back saying that it's done, and indeed you see it here on the left-hand side. Yes. Now, when you have so many schemas, it often is useful to establish one default schema, right? The schema that I'm just using today and for the next couple of weeks, right? I don't want to always have to say, oh, this is the schema that I'm working with, right? So the easiest way is to just double click it, When you double click it, it becomes bold, right? If it's bold, then that is the default schema, meaning any commands that you now issue, right? The assumption is that that's the schema you're talking about, right? All right, let's see. All right, so yeah, a database create a schema. That's the default schema. We double click the table. So let's create our very first table. All right, so tables is going to be our mechanism by which we collect data points that are somehow related to one another, right? So if we want to capture all the movies, we would put it in a movies table, right? We want to capture all the actors, we would capture it in the actors table, okay? And then all the Oscars and awards and whatever, right? Whatever we capture, if the data points are related to one another, we want to put them in a single collection, right? Those data points share the fields, right? The data types, right? They all have all movies have a title, all movies have a plot, all movies have a poster, right? And have the ratings on Rotten Tomato, blah blah blah, right? All those fields describe a single record of a movie, right? And they all live in the movies table. Make sense? So to create a table, it's easy. Either right here, notice that there's four under the schema. There are four things. One is the tables. So again, tables is going to be the main place where we put our data. The data was going to live in rows that are part of tables. When they were thinking about this, of how is it to think about data, folks were thinking about breaking up data into tables. Okay, obviously, this is an abstraction, right? There are no real tables, there are no real rows, right? Everything ends up just being zeros and ones in the file system. But the abstraction, right, is that we think about the data being split up into tables, just like when we program in an object-oriented language. There are no objects, there are no classes, right? There is no inheritance. All that is an abstraction layer, that allows us to think about problems in a particular way, in different layers of abstraction, right? I can think about the problem at a very high level, right? Or I can think it about, at a very minutia, right? And object orientation allows us to create these, self-contained modular pieces that we can then put together as Legos and build, more and more complex things. So all these abstractions are ways to manage complexity. How can we deal with an ever-growing piece of software, right? That is more and more classes and more data. Okay, well, I'll break it up into tables, right? So all these abstractions is ways for us to, compartmentalize or put things in boxes. So yeah, tables, that's where we're going to behave all the data. Views, as I mentioned earlier, are virtual tables, right? Where, you might have broken up the data into multiple tables because you were trying to normalize, right? But now it's inconvenient for the person who's actually consuming the data. Because if they have the students over here and the grades over there and the courses over there and sections over here, right, and departments in that table, and they want to come up with a registrar's office, report on students and how, whether they're going to be make the dean's the dean's list, right, this week or this semester, right? Oh well, they're going to have to go and join all these tables, right? It's very inconvenient. So views allows us to say, well, what if there were a table called dean's list, right, that goes out to the students table, and it goes out to the grades table, and it goes out to the sections and the courses, and it joins all these things together, and it aggregates all the data, it does all the averages, the mins, the max, right, and it puts everything into one single place, right? Something that looks very much like a table, right, where they have the one of the columns is the students, the next column is their grade average, blah, 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 what year they're going to graduate, and all these things accumulated from a whole bunch of tables. Yes, right. But now you have it all in a single nice convenient view. And views they look and behave a lot like tables, but they're not tables, right? They're virtual tables. Then we have store procedures and functions. This is where we're going to spend some time programming the database, right? We're going to be writing code in there using, SQL programming language, right? Store procedures and functions that will allow us to use functional programming, for loops and while loops and iterate and if statements and switch case, things that you would normally find in every programming language. Yes, we'll spend some time in there, and that's where they would live. All right, so tables, like we can create a table from here, either create a table or, right, having selected the schema that we're working with, we can say create a new table up here, right? So this brings you to the new table screen, right? Again, this user interface is just a convenient way for writing SQL. I could literally write this, and later we will, right, by hand. We will write the SQL statement ourselves. But for now, let's use the user interface. It'll write the SQL for us, and then we'll say, yep, that's what I want. And it'll send the command to the server. All right, so what table are we creating today? The courses table. Right, so let's create a courses table. All right, so the naming convention that we're going to be following is that in SQL, the names of the tables are going to be nouns, right? All the tables are going to be nouns, right? And they're going to be plural. Courses, okay? Not when you're doing Java, right? If you're creating a class in Java, typically it would be also a noun, right? But typically the class would be singular, right? So Java has a different naming convention. C# has its own naming convention. Python has its own naming convention, right? Each language, each stack, each technology stack has its own nomenclature, right? So in SQL, we're going to be using plural, singular, all lowercase, right? If it's a compound word, right, my favorite courses, right, then we'll put underscores between the words, right, for the compound sentence, okay? So either a noun or a noun phrase. It could be a noun phrase as well. What else? Also, all lowercase. So SQL doesn't care about case, right? So you could mix and match case. It will ignore the case, right? The user interface will keep it just for your convenience, but logically, it doesn't really care about the case, right? That's why we use underscores in between the words, as opposed to in programming languages, that most programming languages are case sensitive, right? So in other programming languages, we might use camel casing, right? Where if it's a compound word, we usually have the first letter of each word capitalized. Yes? Don't do that here, right? If you're doing this in C# and if you're doing it in Java or any program like that, that's fine. You do camel casing. Yes? But here, because those languages are sensitive, not SQL. So yeah, don't do camel casing here. Okay, courses. Column, one of the columns I'm going to be using for all tables. It's not required, but it's strongly encouraged, right? It's the ID field or the ID column. This ID column is to uniquely identify each one of the records, right? So here we're just describing, right? What are all the fields that describe a course? It's a course. What does a course have? Well, the course might have a title and the maximum number of seats, right? When it's a start date, right? What if it belongs to a particular college? Yes, who's going to be teaching that course? So all those fields is what are describing my course. Yes, one of the fields is going to be the ID field, right? Which is going to be a unique field that uniquely identifies our records. Okay, I'm going to say, notice that it defaults to an integer, right? And I say enter. Notice that it also automatically selected these checkboxes, right? PK, NN, right? Which mean PK means primary key, and NN means not null, right? So it's so it's already guessing that this is the unique identifier for the records, right? And unique identifiers are very important, right? You know, and you know, we all are mostly defined by our unique identifiers, right? You know, we walk around with a whole bunch of unique identifiers. You know, we have our student IDs, right? We have our phone numbers, we have our social security number, we have we have all credit cards with a whole bunch of unique identifiers. So we are like a collection of IDs, right? That unique identify us, right? And unfortunately, it's because there's nothing really unique about us. If you say, well, what about my name? Is my name unique? So, well, it depends in what context. Maybe in this room your name might be unique, right? But what about the university? Is your name unique within the university, right? Or within the town, or within the country, right? And so you start needing to have more and more fields to make you more and more unique. Yes, and so oftentimes there's no way to guarantee that I can uniquely identify you, right, by your field. So we oftentimes just we fall back to a lazy way of making unique by just assigning you a random number. Okay, we sort of do that with phones, right? Again, depending on the context, 4 digits for a phone might be enough at some point, right? But then maybe you have more than 10,000 folks, right? And say, well, no, let's add 3 more digits, right? And then I say, well, no, that's not enough, right? Maybe we need an area code. That's another 3 digits, right? And then when you expand it even more, well, no, we also need like a country code, right? So we add another digit, right? And we keep going and going. And when Elon will put colony on Mars, then we'll need a planet code, right? That will identify uniquely your phone number, right? And so on and so forth. As the context gets bigger, you need more fields, right, to make you more unique. So, or you just randomly generate a unique identifier. So that's what this is. I'm also going to select AI. AI meaning that's not artificial intelligence. Means auto increment. Auto increment meaning either. So if I don't have that checked, then that means that I am responsible of choosing what that unique identifier is. Or I can be lazy and I say, I don't want to deal with this. I'm delegating this to the database. Hey, database, you figure out what the unique identifier is. Just maybe start just at 1 and then just keep going 2, 3, 4, 5, auto increment to the next value, right? Each database is slightly different. Oracle uses what I call sequences. Like it's an infinite sequence of numbers, right, that it pre-generates, okay, and then there are unique numbers that are plucked from the sequence. So it's a completely different way of doing it, right? SQL Server uses identities. So each database is slightly different, right, on how is it that it uniquely identifies its records. What else? You might have you might have a title. Varchar is also a very common data type. Notice that the data type is saying, and we have a whole bunch of data types, right? We have varchars, ints, dates, floats, Boolean, blobs, right? There's a whole bunch of data types, and we'll go over some of these as we go, right? But the most common ones are ints, varchars, and floats, right? And Booleans, okay? Those are the most common, or dates, obviously, right? And we'll use them as we go. But varchar is for strings, and you can say how many characters you want. So 45 characters. All right, so let's say apply. Notice that it writes the SQL. That I could have written this myself, right, by hand. I could have done that. But for now, we'll ask the UI to write it for us. And there it is. We can look at it and notice that the command is to create a table. Then that's the name of the table. It says which schema is it creating in, right? It's under cs5200, right? Here's my ID, which is not null. It's an integer, right? So 0, 1, 2, 3, all the way increments, right? Not null means that it's required, right? You have to give me a value. I have to have a value Otherwise, I'm not going to let you create the record, right? Also, notice that it has the auto anchor because I'm lazy. I wanted to create it for me. Title says that it's varchar, so it's a string of 45 characters maximum. It'll truncate anything further than 45 characters. Null meaning that it's okay for me to not have a value. This doesn't mean empty string, okay? It doesn't mean 0 or -1 or any other flag that might mean empty. It literally means that there is no value, right? It's as if somebody would have just not filled a form element, right? I don't know what value. I can't guess at it. And also I've declared the ID to be primary key, right? We call all these things that's an integer and not null, and it's a varchar or a primary key. We call these constraints. We're saying this piece of information, this field, it has to do this, it has to do that, it's this, it's not that, right? We are constraining the possible values that you can put in that field. Also, behaviors. We're establishing some behaviors. The fact that I'm saying that it's primary key, right? That opens up a whole Pandora's box of what it means that field. One of the things that it means is that it has to be unique, right? You can't have two IDs that have the same value. Just like, we can't have the same social security number unless you want to pay my taxes, right? It also means that it's going to, not only is it unique, it's obviously also required, right? You have to give me a value, but also it means that you can have two records, right, that are somehow related to one another, right? Maybe an actor is related to all these movies, yes? And the way the relationship works is that the actor will have a primary key that uniquely identifies a particular actor, right? Arnold Schwarzenegger, and then you have a movie, right? Terminator. And the way the relationship happens is that the movie will have a foreign key, right, that references the primary key of the actor, right? So that you'll know, oh, what actor was it in this movie? Ooh, that actor over there. Okay, and the way the relationship happens is that Arnold has ID 1, 2, 3, and then Terminator has the foreign key saying that the actor is also 1, 2, 3, right? And that's how we establish a relationship. Yes, right. But then the behavior that is enforced by primary key, right, is that if you try to remove Arnold, right, if there's a movie related to Arnold, it won't let you remove Arnold. Okay, right? Because it says, no, if you remove Arnold, right, you're going to leave this movie orphaned, right? You're going to have the movie referencing something that doesn't exist anymore. Okay, so it'll stop you. It says, no, you can't do that, right? Because then you're going to have an inconsistent relationship, right? Just like if you try to remove a directory that still has files inside, right? The file system will stop you. It says, no, you have files in there. You can't just remove the directory. You first have to remove the children before you can remove the parent. Same thing here. So primary keys and foreign keys establish that kind of relationship, right? And if it would allow what it's called is maintains referential integrity, right? It makes sense to make sure that the references are good. All right, so we'll apply. It's done, and you'll see now that we have the courses here on the left-hand side. Okay, we have the courses. Let's see, it's 7:30. Let's take a short break, right? 5-minute break. Everybody, if you need to go to the restroom or whatnot, or get a drink, and then we'll come back and then we'll continue. All right, awesome, thank you. We're breaking for a couple minutes. Okay. All right, so let's continue. All right, so all these exercises that we're, yes.
I have a question about the primary.
Yeah.
Is the primary key associated with the unique column?
The table can have any number of primary keys.
Okay.
By default, there are no primary keys, and the database will not force you to have primary key. Which can easily get you into trouble where you might have 2, 3, 4 records that have all the fields have the same exact values, and the database will be happy to store a number of records that have identical pieces of value for all the fields, but then there's no way to distinguish one from the other. If you say, give me the records whose field is so and so, it'll give you those 4 records. If you say update the record whose value is this, it'll update all 4 records. Or if you say delete the record whose value is whatever, it'll be all 4 because they all meet the same criteria. They're completely indistinguishable between them, right? So the way to individualize or to make the records unique is by creating the primary keys. And you can have one primary key, which you can have just a single primary key like we're doing here, just one field. Or you can say, these 3 fields constitute my primary key. We call it like a compound key. Yes, yeah, I'm sorry, yes. Columns or fields, right, I'm using the term loosely, but yes, they mean the same thing.
Does the table have multiple foreign keys?
Yeah, so right, exactly. You could have these 3 fields is our primary keys, and these other 3 fields or 4 fields foreign keys, right? And by primary key means that there are other tables that have foreign keys that are referring to your primary keys. And in that record, the foreign keys in that record are presumably referring to other records that live elsewhere, right, in some other table. Yeah. Or we'll see some more advanced implementations. You would have maybe records in the same table, right, that have foreign keys to primary keys in the same table, right? So they're referring to records that might live elsewhere, in the same table, right? So for instance, you might have an employee table, right? And then you might have, who's my manager, right? Now you can create like a hierarchy where you would have a foreign key that is referencing the same primary key in the same table, right? But it would be some other record, right? Like these 10 employees have the same foreign key value pointing to the same manager in the same employee table, right? And that manager and several other managers might have the same manager that point to their manager at the top, right? And then you creating this hierarchy all the way to the board of directors or the CEO, who they don't report to anybody, right? Nobody manages them, right? And that's the root of the hierarchy where the manager is null, right? The foreign key is null, so there's no navigation up. Make sense? Which this brings up another challenge that will come up later when we'll talk about ORMs and how you map the world of the flat relational database with the hierarchical object-oriented world, right? Because in the object-oriented world, the relationship between a parent and a child, right, usually is implemented from the parent to the child, right? You might have manager, right, or you have an employee, right, who's a manager, and then in there you might have an array of employees that manager manages. Yes, and so that array maintains a reference to a whole bunch of other object instances, right? So it is the parent who knows about the array or collection of children. Yes? Usually children will not have a reference back to the manager. You can, but in general you don't, right? You navigate from the parent down to the children, right? If you're doing an object-oriented programming. So whereas the opposite is true in relational databases, right? It is the children who have foreign keys that point to their parents, right? It says, well, I know who my parent is, and I have a foreign key who my parent is, but the parent has no idea who the children are, because the parent can't have an array of references, to their children, right? So it's backwards the way relationships are built in relational world, right, and where they're built in programming world, right? So that's also one of the impedances, right? That one of the challenges that we find, where how do you map a flat relational world to this hierarchy of objects that are flying everywhere, right? So we'll talk about that, some of those challenges. Yes. Yeah.
They need to have all three columns as foreign keys or one of them.
No, you can only reference, if you want, you can just reference one, you can reference two, or you can reference all of them in compound. And we'll talk about why would you do one or the other, right? And in one of the cases, you could be breaking, one of the normal forms. You could be breaking the second normal form, which states that if you're going to reference something, you should reference all of them, right? That you could if you don't reference all of them, you can run into inconsistencies, right? Where some of the fields might be dependent. One of the foreign keys might be depending on only one of the primary keys, but not the other, right? And that can create problems with things reference called functional dependencies. Usually, you want functional dependency means that if you have one field that depends on another field, right, and none of those fields are either a primary key or foreign key, right, that's a problem. That can cause you to introduce bad data, right? So for instance, say you have two fields that one is make or brand, and the other one is model, right? And one of them, you could say Toyota for the make, and Corolla for the model, right? Which is fine. That there's no problem there. But because you don't have primary key, foreign key, there's no enforcement of anything between those two fields. You can't enforce that one can reference another, and that if you delete one, you can't delete the other, like you can with foreign keys and primary keys. When they're unrestricted, where neither one is a foreign key or primary key, you can really put any values in there, right? So you could easily enter Ford, right, and Camry, right, which is bad data. There's Ford doesn't make a Camry. Okay, so just because you're just plain old strings, you can type whatever you want in there. Okay, so even though there's a you're not breaking anything, right? They're both strings. Logically, it makes no sense, right? So you have a redundancy in there that you need to split. It says those two fields can't live together. One of them has to live in a separate table, right? That has to be, you have to break it up into, you have to normalize it, right? And it has to become a primary key, where you have the table of all the brands, right? Where you have Jeep and Toyota and Honda only represented once, as opposed to a field where you're pasting Ford many times, right? And so and then it allows you to create inconsistent data. But if it becomes a foreign key, now you can enforce rules. Yes.
So that, like using your example, the Ford can be like the primary key, and then that can reference
exactly
all the models that they make.
Right.
Foreign keys, and then can those same foreign keys be primary keys to other?
Yes, they can. Yeah, right. Exactly. You could have fields that are both foreign key and primary key. Right. Yep. And that allows you to create one-to-one relationships. Yeah, we'll talk about all the different combinations. Yep. Excellent. Right. So all these exercises that we've been doing of creating installing a database, creating the schema, creating the tables. We're about to start inserting data, retrieving data. That's all part of the first assignment, which is due the 19th. So this Sunday. So let's review real quick. Basically, we've been going through the first assignment, okay, which it asks you to download SQL Server. It asks you MySQL, either for Windows or Mac. It asks you to create a database connection, which we just did. To use the root password, so don't forget that. You can call it whatever you want, but we're referencing here as DB connection. We're asking you to create a schema. I believe we ask you to call it DB design. Please stick to these names so that the TA, because one of the things that we're going to ask you to do is to export your database. Right, once you're done, you export your database. It dumps it into files in the file system, and then those files is what you're going to submit. Right, and then what the TAs are going to do is they're going to download all your files. They're going to import it into their database, and they're going to assume that you call the tables, a particular name, and the schemas you gave it a particular name, and they're going to have a whole bunch of scripts they're going to run against your schema. If you don't follow the naming convention, the scripts are not going to work. All right, so please follow the names. Right, don't get creative. In the project, you can get creative. You can do anything you want in there, but for the assignments, just to make it easier on the TAs to grade, please follow the naming conventions. Okay. Yeah. So create a schema. So this is walking you through all this, and one of the first tables we're going to ask you to create a table. I believe it's the users table. Notice the nomenclature. We're going to use this nomenclature throughout the semester. Right? When we say, "Oh, the schema of a table is yada yada," we're going to use this nomenclature a lot. Right? Where it's going to have the name of the table, and then in parentheses the columns or fields. Right? Fields, columns. Sometimes I'll use properties. Sometimes I'll use attributes. It means the same thing, right? It's what describes the things about some concept, some noun. Right. So users, it'll be an ID for its primary key, and then first name and last name. Notice the underscore in between. Okay. So we ask you to create the users table, and I believe we walked you through doing this. There it is. So ID, first name, last name, primary key, and not null, auto increment. Here's the command that's going to come out and say, go ahead, execute it. And then I'm going to ask you to insert some data in there. So most of our assignments are split into 3 parts. Okay. So the assignment will first handhold you through an exercise, right? And we'll tell you exactly what you need to do. And so you'll go through that, complete that. That's going to be part of your deliverable, right? Usually we'll ask you save it to a file, XYZ, right? Once we handhold you through the whole thing, we describe a problem to you, based on what we just did, right? But then we ask you to do it on your own, okay? And oftentimes we label it as, now you try it. Okay, so we first handhold you, then we ask you to do it on your own, right? And the very last part, there'll be some little a challenge, okay, where we don't handhold you at all. We just describe something, and then you just do that part, okay? Yeah, and then you upload all these files. All right, so then so let's do this. So let's create this users table. Let's see. So let's create the users table. So users, and then the ID, which is auto increment, and then first name, bar chart, that's good. And then last name. And we say apply. That looks good. Why? It's done. And notice that the users table is created here. Right. Now the users table, we can retrieve the content of the users table. Well, obviously we know it's empty. We haven't put anything in there, right? we can either right click and say select rows limit 1000, right click, right? And it writes for us a query string. It writes a select statement for us. Okay, it sends it over directly to the server, and it comes back. It comes back with the result, all the results of the rows that match your criteria, which right now it's empty. No rows came back. So down below we see the result grid. So the data that came back from the server, it formats it in a table format. Okay, with rows and columns. Right now it's empty. There's nothing there. You can enter some data here. Again, it's a UI. This is going to allow me to send commands to insert data, send it into the database for me. Right. Again, I could be writing all this by hand. Right. I could have, instead of doing this by like this, I could have just said, I could have written it myself. Select star from users. Okay, and select it and run it, and I would get the same thing. Yes. Right. Just at the UI of being able, just gives me that added convenience. Okay. All right, so let's insert some data. I'm going to use the UI to do that. And I'm going to leave the ID blank because I had configured to be auto increment. Yes. So I'll leave the database to choose for me the ID. If I had not chosen auto increment, I would have had to provide an actual value for this, right? And I would have to guarantee that that value was unique. All right. But I'm lazy. I set it up to be auto increment. I don't have to provide a value. And then first name, we'll say Alice in Wonderland. And we'll do Bob Hope. Enter. If you don't enter, right, it will not assume that you have a value in that field, that column, right? It's kind of finicky. The user interface is kind of adamant about that. A little bit anal. Okay, so we can now say apply. So it writes for us this command. Again, we could have done this by hand. And the command, we'll come back to what these commands look like, but it's insert into a table. The table is inside of the schema. And then the first two here are the columns, and then the values for those columns, right? So for the first name, it'll be Alice, and for the last name, it will be Wonderland, right? And then the same thing for Bob Hope down below. Notice that the ID field is not here. And it's okay because I declared as auto increment. So this will work. But if I had forgotten to put the auto increment, these two inserts would fail, right? It would come back with an error saying, field ID is missing, blah, 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 whatever. Okay, but this, because I declared as an auto increment, this will succeed. And then now we have the fields. Notice the IDs are there, it says 1 and 2, right? That it came up on its own. Right. Same thing if I go back to my query that I had written by myself, right? I can rerun it either by just typing, selecting the what do you call the lightning bolt, right? And what it does is that it executes all the commands in this file, right? Which right now I only have one command, but if I had a whole bunch of commands, it would have executed all of them, right? Right now, it only executes a select star from users, and notice that it comes back with the same value that I have here. Yes? Okay. If we want to execute a single row, because we have like 30 select statements, right? A couple of selects, a couple of inserts, a couple of updates, a couple of deletes, but I only want to execute just a single one of them, I can just highlight what I want to execute and run that. And it only runs that. So careful, right? If you don't have anything highlighted, it'll execute all of them. And maybe that's not what you mean, right? So if you want to, instead of having 20 commands in a single file, you can just create a new file, right? Have separate commands in different ones, right? I can have my inserts in one place, the updates in another, the selects in another, right? So that I'm sure not to execute everything all at once. Make sense? All right. Yeah, so throughout the assignment, I do ask you to create multiple files, right? As you go through the exercise, and to save them. And you can save them by, just say, either clicking the save button or Control S, right? And you can save that file, the content, into whatever directory you want. Make sense? Okay. All right, let's go back to here. So we created users, I believe, bar chart, yada yada yada. We inserted, right? Alice and Bob, and retrieving. You can just say select star from users. So star means, so usually the select takes a couple of arguments, right? The first argument, that star, means what fields or what columns do you want, right? And you can specify which columns. I want the ID column and the last name column. I don't want the first name, okay? Or if you want all of them, you can either specify all of them explicitly, or you can say star, meaning I want all the columns, star. And then you have to specify, well, you want all the columns from what table? You have to tell me which table. So the from clause, we call this the clause. From clause allows you to specify which tables do you want, right? And we can either specify a single table or multiple tables, right? We can specify, because we might have some columns in this table and some columns in some other table. They want to bring them over, right, and combine them into a single result. Yes, right? For the most part, we're going to be doing a single table for now. Later on, we'll see how to combine multiple tables. And plus, there's a where clause to this, which we'll see a little later, right? That allows us to specify, well, maybe I don't want all the users, right? I only want certain users, right? And that allows me to filter. Okay. All right. So we did that. Okay. Now we can do records by some criteria. So the where clause allows you to specify a criteria, right? You might have thousands and thousands of records, right? Of rows. Now, if you do select star from my table, it'll come back with all those thousands and thousands of records. Maybe that's not what you want. You might say, well, give me the employees, right? Right, of which I'm going to give them a bonus this year, right? Who worked overtime and blah 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 blah, whatever. We've been with the company for so long, yada yada yada. Right? I can specify in the where clause the criteria that will filter out only those records that meet my criteria. Make sense? Okay. So this obviously internally, what's happening is that this is a for loop, right? It's iterating over each record, yes, and asking each record, does that record meet the criteria? Right? If not, it'll skip over it, right? And then it'll go to the next one. It says, well, do you meet the criteria? No, 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 yes, right? And it picks out that row that meets the criteria, and then it goes to the next one, right? Now that's very time consuming. If you have, thousands, hundreds of thousands of records, these are stored in the file. You're gonna have to read those file in and iterate over that. I mean, that's very, very time consuming, right? But you should think of it, this is a for loop. Right? This is iterating over each one of these. Okay, and later on we'll see, well, what's the performance of this, right? How can it be better? Okay. All right. So in this case, we're gonna take this query and let's go back, and we can just paste it in here. Select star from users, where users dot first name equal Alice. Okay, right. Again, if I click on this, it comes back with the 2 records. But if I select that and I run it, it'll only return that one record, right? That met the criteria. Yes. Okay. Notice that the strings are declared using the single quote, right? Careful, it's a single quote, not double quoted, and it's the equal, not equal or triple equal or anything like that, just simple equal, right? And notice the dot notation, right? The dot notation. And now here I'm specifying users dot first name, but because we have a single table, we only have the users table. It's redundant to say users dot first name, right? It's obviously from that table, so I could optionally just leave it out, right? and this would still work. Yes, it's when you start having multiple tables that you have to now specify. Ooh, you want to do what with what field or what column for what table? Yes, right. Then you have to specify and using the dot notation, right? Yes.
If we have different tables, like there's only one table that has first name.
Yep.
inclusive,
Yep.
do we still need to specify
Right, you don't have to, right? Yeah, if you have two tables and all the columns in the table are unique, right, there's no inconsistency, then yeah, you can leave out the prefix. You can leave out the prefix, right? But if you have two tables that have name and name, right, then you have to specify. You can also name the you can give them you can give tables aliases, like for instance, you. Now you is an alias to the table users, right? So that you can now use the alias instead, you dot first name. This is useful if maybe the table name is very long and you just want to be able to use the alias. But it's but definitely it's very useful for when you have hierarchies, right? When you have a table that references itself, like the manager's table or the employees table, right? Where you might have records with a foreign key that reference records in the same table in the primary key, right? And you want to be able to say, hey, I want the employees whose foreign key, right, is equal to the employees that have a primary key, right? So that I can say, well, so that I can group together the employees by manager. Yes, give me all the managers give me all the employees for this manager and the employees for that other manager, right? And the only way to do that is so I can say, well, when the foreign keys of some records are equal to the primary keys of other records, but it's in the same table, so you need to mention the table twice, right? As if they were two tables that you were joining them, and you have to say where table 1 foreign keys are equal to table 2 primary keys. But table 1 and table 2 are actually the same table, right? And the only way to do that is that you have to name them. You have to you have to do aliases, right? So aliases are very, very useful, for hierarchical data structures. All right, let's continue. So let's see. We got Alice. Now there might be multiple users who have Alice, right? Or maybe you have, let's see, maybe you have multiple folks that have the same last name. Okay. And maybe we have the cat in Wonderland, who's a family of Alice. And let's insert that. Right, and if I go back and I query and say that I want, select star from users, where last name equals Wonderland. Okay. Now, if I run this, it comes back with two records. These are two folks that have the same last name, Wonderland, right? And it will retrieve all the records that meet that particular criteria. Or if I want to retrieve a particular record that I know it's unique, that might have, I can retrieve them by their unique identifier, 2. There we go, right? So I know that Bob has that particular user ID 2, and then I retrieve just Bob, that one record. Make sense? Right? It makes sense that if I retrieve by a primary key, I'm always only ever going to retrieve a single record, right? By definition. Yes? And if I retrieve by something that is not a primary key, then it's very common that I could retrieve many records, right? That meet that criteria. Yes? So we're going to go back many, many times, revisiting, how things behave if you're working with primary keys, and how things behave when you're not working with primary keys. You have to be careful. Queries that run very, very fast, right? When you use a primary key, might run very, very slow right, when you use non-primary keys. Okay, so it says, wait a minute, it's the same query, right? But if I use these fields, it runs really fast. But if I use these other fields, it runs really, really slow, right? And so that's gonna allow us to choose, how is it that we split this up, right? And create indices and define primary keys depending on the performance that we want to achieve, all right? Okay, all right, so it asks you to do that. Notice that at each step, it asks you to create a particular file, right? And save your query in there, right? Create a file called select users by first name. I think before it says, select all users. Whatever it asks you to do, right? Just follow the instructions and copy and paste the content in there. By ID, exporting. Oh, and then finally, at the end, I believe it asks you to export the whole data. And to export, you can go to server, data export, and then you can choose the schema. And hello. Oh, there we go. Okay, and it shows you all the tables, right, that are in that schema, right? Courses and users I have here, and then I can say where do I want to export it. Users, Janu, documents, dumps, and then it'll create a directory with today's date, and then it'll dump I believe one file for every table. All right, so let's do that. Let's export it. Start the export. Okay, so it's done. Where did it put it? Done, blah, 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 blah. So let's take a look at what's in there. Channel. User. Where's users? How do you go to users here? Documents. Oh, I could just go to documents. Okay. Dumps and today. All right. Notice that it creates two files. Right. Let's take a look at these two files. Courses, we didn't do anything really with courses, right? So there's not going to be anything very interesting there. So let's take out users though. There it is. So this is what gets exported. So what SQL is going to do is that it's going to export enough information, right? Enough information that somebody can use this SQL to recreate the original database. All right. Okay. So for instance, what's going to do here, for instance, is going to say, well, this came from a table that was called users, and it had 3 records, right? Alice, Bob, and the cat. Okay. So I need to be able to recreate that. And one of the things that it does is that it cleans out. It says if there's already a table called users, I'm going to blow it away if there is, because I'm going to create it brand new from whatever I'm importing. Right. So it drops the table if it exists, users. And then here's the command to recreate the table with the schema, the original schema, with the ID, the first name, the last name, the primary key, the correct data types, right? So exactly how we created it, right? And then it's going to populate the table, right? Make sure that it's going to have the same data that was there originally, right? And in particular, it's going to say, it's going to insert into the users table after it creates it. Notice that it locks the table. It says, I'm going to write to the table. I don't want anybody else writing to this table, right? Because you can have other things happening, other users logged in, inserting or deleting or updating. So it locks the table. Makes sense that make sure that other users are locked out. And it inserts 3 records. The first record, Alice Wonderland. Bob Hope and Cat Wonderland. And then it releases the lock. Releases the lock, and it's done. Boom. Now I have my users table. So that's what the TAs are going to do, right? You're going to dump your tables, and the TAs are going to import anything that you've created so that they can validate and grade you. Make sense? Yeah. So this first assignment is pretty simple. Just want to make sure that everybody is able to have a database running. They can do some simple SQL, right? And then we can start playing around with the database. All right. Any questions? Pretty easy, right? As part of the assignment, there'll be an upload where you can upload the files. Right? And so I think there's 4 files that I asked you to upload. Let's see. Yeah, these 4 files. All right. Yes.
With primary keys, if you try and add a insert a new piece of data into a table using a primary key that already exists in there, will it overwrite that?
No, it will stop you. Yeah, it'll stop you. Yep. And like I mentioned earlier, even when you start deleting the database or deleting a table, right? It'll verify, make sure that if that primary key is being referenced by some other table, it'll stop you from deleting, right? So oftentimes you have to delete things in a particular order. Just like you would empty a directory, you will first empty a directory before you delete the directory, things like that, right? So things have to be done in a particular order. So yeah, for instance, there's an assignment here that asks you to create all sorts of things and start deleting, and then you have to figure out, oh wait, this has to happen in a specific order. I can't do it any way I want. Yes.
Is there a way to force delete it even though it says no?
Yeah, there's commands to drop everything. Yeah, yep. All right, excellent. Let's keep going. Tables, blah, 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 create a user. Oh, another thing is one of the things that you might want to do, I believe I asked you to do this, is to create another user, right? So there's a root user, right? But you might want to create another user that's specific for this course, right? That has specific specific things that it can do. Administration. Huh? Object schema. Why can't I see where's my? Interesting. Yeah, why is it like, oh, it's not connected. Okay, never mind. Here, I'm back where I was before, this connection. Right, so if you go into administration, you can create other users. You say users and privileges. So let's create a user for this course. So we'll say add account, and this will be login name. I'll say cs5200. And I'm going to be lazy. I'm just going to use the same password, cs5200, so I don't forget. And then also, you can configure what can this user do, right? And again, it depends, right? Because one of the things that databases need to allow you to do is specify first an identity. Who are you? I need to know who you are. And once I know who you are, I need to give you an authority. So there's authentication and there's authorization. Right? Once I know who you are, what can you do and what can't you do? Right? So for example, if I'm a professor, I should be able to see my courses. I should be able to see my sections, all the students. I should be able to give you all grades, but I should not be able to change somebody else's grade in some other course, in some other section, right? So the database needs to be able to support, right? That yes, I know who you are, but then these are the things that you can do, but not other things, right? So one of the ways you can do that is by creating these users, and then you can give it the roles that they can that this particular user can have, right? You could be the dean, you could be a staff, you could be a faculty, you could be, and depending on your role, you could do certain things, but not other things, right? In the registrar's office, you can see everybody's grade. right? But if you're faculty, you should only be able to see the grades for the courses that you're teaching, right? And nobody else's, yes? So depending on your role, you have more or less. Here, I'm gonna give cs5200, I'm gonna give him super user capabilities. They'll be able to do everything, right? So I'm just by clicking DBA, he's a database administrator. He has got like powers. He can remove everything, read everything. He can do everything he wants. And on the right, you see that all the privileges that this super user has, right? But you could certainly be less than this, right? For instance, depending on the database, you might allow only read only, right? If it's a particular user, yes, they can consume the data, they can read all they want, but they can't update the data, right? Okay, so it depends, and you can create roles, and then depending on that role, certain privileges are for that particular role. I'm just going to apply, and now I have a brand new user 5200 that I can remember the password. I can now log in as cs5200, so I can create a brand new connection, right? Called cs5200 and use instead now cs5200 test connection with same password, cs5200, and say okay. Successful, and say okay. So now I can have two connections. Now these two connections are two different users that are logged in, right? One is a user called your username. That's one user. And the other user is called cs5200. Yes. I'm sorry? What a connection is? We just did. Right. So when so the client, right, is establishing a TCP/IP connection with the server, right, and it can have multiple connections at the same time, right? One connection that is talking to my server here locally, and maybe another connection to a server that's halfway across the world, right? And the same like a browser, when it goes out to a server, retrieve an HTML document to render in a browser, right? It does a TCP HTTP connection to a server, right? And then it receives as a response, right? These all use client server architecture, right? Where I send a request over the IP, right? And then I wait for a response from the server, right? And usually these connections are considered to be live connections. They maintain a session, right? So that once I log in, I'm giving a token, and then I use that token every time I send a request, so I know it's still you, right? And the server will maintain some state information about you, knowing that this connection has been authenticated, and it has some kind of timeout, right? That says, well, if you keep requesting within the 5-minute mark, right? I will assume that it's still you, and you don't have to re-authenticate yourself, right? So it maintains this session, and part of the session, it also has any variables that you might declare, any statistics about our communication will be part of that session, right? And usually those sessions time out. Like for instance, if you haven't sent me any requests within the last 10 minutes, I will assume that you no longer are in the session, and I will render your token invalid. So if you try to use the same connection, it'll fail, right? It'll ask you to re-log in. That makes sense? Yep. Okay. Yeah. So here are two connections, two live connections, but from two different users on the same server, right? And the server can, MySQL is designed to have hundreds, thousands of live connections at the same time, right? But you have to be careful, right? Because the more connections, the harder it is for the server to maintain all these live connections, right? It's resources, it's memory, it's whatnot. So sometimes we use what is called pooled connections. So the connections are live, and they're put into a pool. And then if you have multiple threads, maybe hundreds of threads, instead of each thread having its own connection to a database, right? They will use a pool, a connection from a pool, right? So the thread comes in, I need to talk to a database. It'll be giving a connection from the pool. The thread uses a connection and then releases the connection. It goes back into the pool, right? And then you have multiple threads right, that are trying to connect to the same database, right? But they might reuse the connection over and over and over from multiple threads that are running, right? You know, I mean, there's pretty powerful configurations that you could do, clustered clusters, databases. It can throttle these connections, like for instance, depending during the day, you know, as the, you know, as the traffic changes over the day, the pool might grow and shrink, right? If there's more users, it gets busy, the website gets busy, or traffic increases, right? You might need more connections, right? So it'll increase from 10 connections, it'll increase to 20 connections, right? So it can throttle the performance of the. Obviously, it means that you need more RAM, you need more disk space, you have to be able to support that, right? And then as the day, you know, progresses and you have, you know, less and less connections, usually the connections are released, right? And the memory goes back, and any memory space, any disk space is released and given back to the virtual system. So yeah, these can be really tweaked for, you know, maximum performance. Anyway, one of the assignments asks you to create multiple connections, right? Logged in as different users, right? And then now try both users to try and write to the same table at the same time, right? And see what happens. Right? You know, they're both competing for the same resource, right? And so one of the exercises asks you to work with transactions to lock the table while you're writing, right? And then others are locked out, and I can't read, I can't do anything, right? So you know, just to learn about, you know, multiple users using the same resource. Anyway, let's go back. So okay, we can create users. Excellent. All right. All right, databases. Is that the one? Okay, let's take a look at database systems. All right, so we've gone through most of the assignment. Let's get back and just recap. So databases, right? They're it's basically a collection of data stored in computers, and typically they're organized into records collected into what we call tables. Each one of these tables, usually a table will it has the equivalent of a data type, right? Like employee, right? Or movie or actor, right? It's like a data type, you know, just like you would represent that in a class, a movie class or an actor class. It's a data type that you create using an object, right? Or a class. The equivalent here is that you do a table. So later on, we'll see that a table in SQL is the equivalent of a class in an object-oriented language. Yes, right? And an object instance in the object world is the equivalent of a row in a table. Yes, right? And as we progress throughout the semester, we'll make that equivalence more and more literal. So for instance, you might have the employee records, right? The student records, the medical records. So we're going to be using an example throughout the semester. It's an academic example where you have the following tables, right? And this will be a recurring example that we'll see throughout the semester. So we'll see a table called students, another one departments, courses, sections, enrollments, right? With these fields or columns, right? There'll be IDs for students, name, graduation year, major ID. So major ID will be a foreign key, okay, that references a department. The department has a department ID and the name of the department. And then the student, we can establish what's the major, what department are they graduating? So it's a foreign key to the primary key, department ID. Then you have courses, right? And also the course knows about what department it belongs to, meaning, you know, it is this department that is teaching that particular course. It has a title for the course. Also sections have their own primary key. The professor who's teaching this, professors are not as important that they might have their own table. Okay, just the username is fine. But again, those kind of decisions, it depends how granular you want to model your data types, right? Okay, it's you know, if the only thing you're capturing for the professor is a username, then it could just be a field, right? But if you want to capture the first name and last name, whether they're tenured, right? What's their office? Well, this will not work, right? You would need a dedicated table, right? So those decisions, right? How granular you want to be and what kind of things are you capturing is what we call the design phase, right? You know, is it just a field is enough, or do I need a whole table, right? Here we went with just you know, professor's not important, username is enough. Notice it has a foreign key. It's referencing the course. So one course can have multiple sections. Makes sense, right? So there is a one-to-many relationship. One course can have many sections, right? And usually, notice how this would be implemented in an object-oriented world, right? A one-to-many would be a course has many sections. Typically, the way you would do that is that the course has an array of sections, right? Here's the inverse, right? Is a section who has a reference to the course. The course has no idea of any sections. Notice that there's no field or column that has any reference to sections, right? It is the children sections that have references to the parent course. See that? It's kind of inverse the way we implement it in relational databases. Down below here, we have enrollments. So enrollments establishes a relationship. Oops. Enrollments establishes a relationship between two data types. It says that that student, which is a foreign key to the student, it's pointing to that student, is enrolled in this section. So section is also a foreign key, right? It's establishing a many-to-many relationship, right? Because one student can be in many sections, right? But one section can have many students, right? So there's a many-to-many, right? One thing is related to many of those, and one of these is also related to many of those, not necessarily the same ones. Make sense? Just like actors in movies. An actor can act in many movies, but then one movie can have many actors, not necessarily the same actors. Yes, and not necessarily the same movies. So enrollments is the enrollments table is sometimes referred to as like an association table, right? It creates associates records in one table with records in another table. So associations can be either between one table and directly to another table, like a one-to-many. One course has many sections, or enrollment just sits there pointing who's related to who. See that? Right? This is the more generic. This kind of relationship allows you to establish any relationship. It allows you to establish a one-to-one, a one-to-many, or many-to-many. Right? It's the most generic type of relationship. Right? Over here, we didn't need to create a many-to-many. Like, you know, a course has many sections, but you can't say that a section has many courses, right? So this is a strictly one-to-many. See that? Right? Whereas enrollments allows you to establish the many-to-many. And indeed, this is the only way that you can establish many-to-many relationships in SQL, right? You need a separate table, a complete separate table that points to two different tables, right? In C# or Java or object-oriented languages, many-to-many could be implemented with one student can have an array of sections, but then a section can have an array of students. There's no need for an intermediate enrollments class. Yes, right? Because one instance of a student can have an array of references to a whole bunch of sections. And same thing for the sections, right? The sections, one single section instance can have an array of multiple students. There's no need for an intermediate, right? Saying that that student is enrolled in that section. The student and section know about each other. There's no such thing that you could do that in relational databases. The only way to implement the many-to-many is to have a separate table, that references two of the records. Make sense? So that's another, as we'll see later on, that's also one of the difficulties, right, of going from a flat implementation of relational databases to a hierarchical implementation in object-oriented languages. Yes, right. And whatever you're going to implement, whatever you're going to code, you're going to end up with some object-oriented language or whatever, right? So this challenge, you're always going to have to face it, right? To say, okay, well, how do I map this flat thing into this, objects, right? They're flying around, right? How do I map these two worlds? Ooh, battery. Kick me out. Damn it. I love this laptop, but it just has terrible battery. Just a second, my laptop just died. Change it. Yeah, just a couple more minutes. Hold on a second. Oh man, it must be tough at this time of night. I don't know how you guys do it. Stay awake, listening to me go on and on. Like, I don't know if am I still on? I don't think so. Okay, I think I'm back in. I think it's still recording. All right. All right. So here's a sample. Here's a sample of the data of some students and departments. Notice notice how the departments are. We have 3 departments: computer science, math, and drama. And they have a primary key here, 10, 20, and 30. Right. And then notice that these are the students. It's a very small university. We have only 9 students, and of which here are the major IDs. See that? So these are referencing the departments, right? We have 9 students, of which 3 are in department 10, 3 are in department 20, and 3 are in department 30. Yes, right. And that's how we establish a one-to-many. One department has many students, right? Then we have sections down below, and the section we have that they all refer to the course they belong to. There they are. These are the 6 courses that we're teaching. Some 2 courses are taught by computer science, 2 by math, and 2 by drama. Right? They are referring to these references here. And we have the sections. We said that we have these 5 sections, 2 sections for course 12 databases. We have 2 sections for course calculus. We have 1 section for elocution, right? And finally, we have the enrollments. We're saying that these 2 students, this 1 student, Joey here, is enrolled in these 2 sections, 13 and 43. 13 and 43. Yeah, so this 1 student is in 2 different sections, whereas this student is only in 1 section. This 1 student is in these 2 sections and whatnot. Okay, make sense, right? So yeah, so the university database, there's a 1 student record for each instance. The enrollment relates these 2, the students and the sections, and the sections know which course they belong to. Now, deciding that we are using these 5 tables, so somebody had to decide why 5 tables, not 6 or 7 or 2 or just 1 big table. Now, who decided it was these 5 tables and these fields, right? So presumably this is the result of some analysis, some certain considerations, and having designed the database this way, right? And that's what we're gonna be teaching for the first week or so, right? On how is it that you would decide this and not something else. Yes.
So it's not a good reconcile to like as IDs or like that. Why is that?
Yeah, I mean, I would have chosen IDs for all of them, just list them IDs. It made it harder to then write the slides. And so it made it easier to add a little S or E or SC. Yeah, no, it's fine. I mean, for primary keys, yeah, that's fine. Yeah, university database. Yeah, it's persistent, right? Some of the features of all database systems is that it's persistent, right? Meaning that if you put the data there and you come back tomorrow, it's still there, right? It's large, right? So you're talking about terabytes of data, huge amounts of data, as opposed to in a program might be running small subset of the data. It's shared, meaning you're going to have lots of concurrent users. It's accurate, it's consistent data, right? That if you're transferring money from one account to some other account, well, there's no money lost, right? If you have $100 in this account and you're transferring to some other account, right, you want to make sure that the data is always consistent. Nobody lost $100, or no one just made $100 all of a sudden, right? That the data is always consistent. Even if from some terrible calamity, right, that the servers go down or the client goes down or something happens, there's always a way to go back and reconcile everything that happened and go back into a previously consistent state, right? So database have to provide that kind of service, right? That it's always accurate. It's usable, meaning it has some user interface that allows you to interact with it and the administrator. Now, how is it that we would store it? What format would we choose? Is this just one big, all these, I mean, obviously these are stored in some kind of file system. And how do we declare that something is a record? And do we use commas or tabs, or how do we format the data, right? Usually we will typically have one table will have one single file that goes along with that table. Usually there'll be additional auxiliary files, right, that will allow us to increase performance for that particular table. Oftentimes that table will also not only have a single table for the data, it'll have also some index file, right, that allows us to improve the performance of a specific table. Yeah, you have multiple users that could be accessing and updating the data at the same time, which increases the risk of inconsistency. What if I go to Kayak or and try to book a seat on an airplane, and the UI is showing me that these seats are available, and when I'm not the only one looking at this, right? There might be another 200 people looking at the same exact piece of information. So how do you reconcile that I click on a seat and you also click on a seat, right? So how do I reconcile the fact that I'm looking at this and I might be looking at stale data, right? Usually any data that we are working with will always be stale, right? It will always be a copy of something that is the truth. And while I'm holding this copy, the truth might be changing, but I'm always working with this copy. How do I reconcile these two things? Yes.
So that's when like movie tickets.
Yeah, right, exactly. So there's this some kind of locking mechanism, right? And we'll see there's like 3 or 4 different strategies of how to reconcile. One is, I don't care, just everybody do whatever you want, right? That's the easiest thing, right? And you only reconcile later, as in, oh, sorry, I know I said it was free, it was available, but actually it wasn't, right? So that's the easiest thing, right? You reconcile later, and you just deal with it with later. Or the most egregious one is that everything's locked. If I'm looking at this, I'm the only one who's looking at this, and I'm the only one who's allowed to interact with it. Everybody else will have to wait until I'm done. So that's the other extreme, right? And there's some gray areas where one of them is when you allow everything, that means that's the fastest, right? Threads are allowed to run anytime. Nobody has to wait for anybody. That you have full concurrency, very optimistic. On the other hand, you have completely synchronized. Everybody's waiting on everybody. There's always a traffic on people waiting on each other. That's that's the other extreme, right? And there's other gray areas on what could be done, and we'll talk about all these other strategies. Yeah, so there's strategies of blocking and getting a lock on either the entire table, or maybe you're locking only the single row, or you're locking to just a single field, right? How granular can you go and allow other things to happen simultaneously while still maintaining consistency, right? Yeah, so databases need to be able to detect when there's a conflict, something went wrong, right? And they need to be able to keep an audit of who's doing what, right? And so that if there's any problem of inconsistency, I need to be able to backtrack, right? And says, okay, what happened? I know you were transferring money to your parents were transferring money to your student account. They said that they transferred $1,000, and but they never made it into your account. What happened, right? So the databases maintain an audit of what happened, so that you can always backtrack, right, and see where the diversion happened, so that you can go back to some consistent state, right? Yeah, so transactions allow you to do all these kinds of things. Authentication, authorization, right, where databases need to be able to determine who you are, but then once they know who you are, what are you allowed to do? Memory management, right? That the database might be maintaining terabytes of data, but it only the actual software can only deal with small snippets of it at a time, right? So it needs to maintain some kind of caching mechanism, right? That as you're querying, you're only really dealing with only a small snippet of the actual total data, right? So how do you do a query that it goes beyond whatever you have cached in memory, right? And go out and actually iterate over the entire terabytes, right, of data. So how do you maintain synchronicity between data that is cached in memory, but as opposed to what's that's stored in the file system? How do you maintain that synchronicity? Also, the data models, and how do you maintain multiple representations of the same data? The file system has a particular representation, usually binary, some kind of binary representation, typically spread over multiple files, right, that are linked together. That's a physical representation that needs to be then mapped to a conceptual representation. We don't want to think about files that are linked and they're binary. We want to think about it in a conceptual way, right? These are tables and rows, right, and foreign keys and primary keys, right? We completely don't want to think about any physical representation. We want to talk about it in a conceptual representation. So there's a file data model, but there's also a relational data model. We're going to stay in the relational data model, meaning these are tables, rows that are related to one another. That's why they're called relational data models, right? Because the records are related to one another, foreign keys, primary keys. So we want to be able to stay away from these things. So before databases, we wanted to query a file system that had tons of data. We would have to read the file, reach records, iterate over each record, right, and find those records that met a particular criteria. Keep an eye of all those records, maybe do a collection, push it into a collection, right, and then maybe average out the values in there and come out with some aggregate value. So we want to abstract all of this into something as simple as, select the names from students where the graduation year is 1997. So obviously behind the scenes, this is what the database is doing, right? It's looping through a whole bunch of files, right, and looking for those records, and it abstracts all this complexity into select name for student where grad year equals 1997, right? So we want to stay in the relational model, in this conceptual model, and not deal with any of this physical system. I mean, there's tons of other data models that we're not going to talk about in this class. I mean, there's graph-based models. There's actually, no, we are going to do object-oriented models. There's hierarchical models like XML. You know, there's real-time databases, right? That you know, each one is designed for other use cases, right? That we're not going to be considering in this class, but there's tons of other types of databases that are out there. We're going to be sticking only with the relational database. All right. I did want to. Okay, yeah. Just one more thing. Yeah. So down at the file system, you know, you're going to have lots of files. Some of them are going to contain the actual data of the student data or the enrollment data. Now, some of that files will also be indices that are auxiliary files to the real data, right? That allows you to create indices to these to improve performance, right? So all these file systems, right? We're gonna stay away from that, and instead, you know, be able to deal with them at a conceptual, you know, in the form of tables. You know, there's a student table, right? And there's the enrollment table and the sections table. Now, underneath, obviously, it's supported by all these other files. And there's also what we refer to as an external schema that is what views allows us to do. Right? Views allows us to create a schema, a virtual schema, right, for users of the database who don't really care about this layer of abstraction. This is too much for them. Just like it's too much for us, that we don't want to deal with the nitty-gritty of the zeros and ones, right? And we abstract it into tables. Well, for them, this is too much for them. It says, oh, you have like these 20 tables. You know, can't you just give me one where that has everything, right? And so to support that, we have views. Views allows us to, you know, for the dean's office, it allows us to group together 3, 4, 5, 6 different tables into a nice report, right? That they can use like a quarterly report or an annual report that aggregates all this data into one nice report. Yes. So, you know, I mean, that's humans. That's what we are, right? We are abstraction machines, right? We understand something. Once we understand it, we package it, right? And then it's a piece of Lego that we can build something even more complex, right? And once we understand that, we put a box around it, and we create something even more complex, right? And we just keep going and going and going, right? And that's all I have for you today. Let's see. Yeah, let's leave it here. Any questions? Yeah, so office hours tomorrow at 3:30. We've been asked to do office hours only remote. I'll be physically here in the university, but I'll be in my office doing remote office hours. All right, that's starting tomorrow at 3:30. The TAs also have posted their office hours as well. Please reach out to them if you're having trouble installing MySQL. They've gone through this quite a few times. They're the better folks to help you. All right, thank you. Good night.